Hello, everybody. Thank you for joining us, and welcome to our virtual workshop on financial mathematics and stochastic analysis, taking place on Monday, the 22nd, and Tuesday, the 23rd of June of 2020. Organized jointly by Instituto de Ciencias Matemáticas, ICMAT, Universidad Autónoma de Madrid, UAM, and Universidad Nacional de Educación a Distancia, UNED. We want to thank our speakers for collaborating with the organization and the dissemination of this workshop. Tomoyuki Ichiba from the University of California, Santa Barbara in the US. Isabel Figueroa Ferretti from Universidad Pontificia Comillas in Spain. Ioannis Paraskevopoulos from Bankia, also in Spain. And Stefan Storm from the Worcester Polytechnic Institute in the US. We will talk about ongoing problems on financial mathematics and stochastic analysis. And besides, we'd like to thank David Lauriere, coordinator at UAM of Gaia project of European Union Horizon 2020 Research and Innovation Program. Also to Laura and Agatha from ICMAT for the dissemination of this event. And of course, Carlos Escudero from UNED, the co-organizer of this workshop, to whom I'd like to give the floor. Thank you very much, Carlos.
Thank you, Mauricio. Before introducing our first speaker, Professor Tomoyuki Ichiba, please let me mention to our attendees that if they have questions, please type them in the chat, and then at the end of the talk, a selection of the questions will be answered by the speaker. Okay, so once this is said, let me introduce our first speaker, Professor Tomoyuki Ichiba. He's from Japan. He's associate professor at the University of California at Santa Barbara. He did his PhD in Columbia University in New York City, and his research focuses on financial mathematics and the theory of stochastic processes. So please, Tomoyuki, when you're ready.
Thank you very much for the introduction, and I'm sorry for the technical glitch. But my name is Tomoyuki Ichiba, and I want to talk about numerical methods in Minifield game for large banking system with defaults. This is a part of joint work with Romeo Elie and Matthew Lauriere. Thank you very much for the invitation to this talk, to this wonderful workshop. Thank you, Mauricio, for organizing all these things. And I'm also thankful to all the medical workers who fight right now, fighting with coronavirus pandemic. Okay, so today I want to talk about Minifield modeling, which takes into account default and recovery of financial institutions. So defaults and spikes can be seen as a particle system of banks. So let us consider n diffusive particles. We consider xt1 to xtn on the positive half line. So we consider particles moving, and each particle represents a bank reservation, monetary reserve. Each xi, xti has a diffusion dynamics, which means we have some drift function b assigned to each xti, and let me call its average xt bar. So xt bar is average of all the monetary reserve in the system. There are n banks. And for the simplicity of the presentation, let me assign unit diffusion coefficients. We can make it more complicated, but for the presentation, let me put 1 for the diffusion coefficients. And we assume this path, the sample path of stochastic process from time t to xti, this sample path as a map, right continuous with left limits. And so these are moving according to some diffusion dynamics. And we consider default, the following default scenario as defaults. The position xti0 of particle I0 at time t0, let's say, becomes 0. So the process is always on the non-negative side, and at some point we assume that xt I naught, the bank I naught, is default, hitting the level threshold 0. This particle I naught or bank I naught is default and annihilated from the system. And each particle j, the other particles or the other banks dragged by x bar divided by n. So at some point there is a default, and then this default generates negative effect to the whole system. So dragged by this amount towards 0, so everyone is going down. And also we introduce a new particle at that moment. So we have a default, and then we introduce a new particle as compensation of this defaulted bank. Again, this is a model, ideal situation to a simplified situation of the real economy, real financial system. This new particle, so I introduce a new particle in replacement of the old particle default. And again, we call I naught. In other words, right now, in this system, the number of particles, the number of banks is constant. All the time, the number of banks is n. And this new particle starts with initial point position x bar t0 right before the default time. So we put xt0, I0 minus is 0 because of the default. And then we restart this process, this stochastic process, as the average point. Okay, so this is a model. I hope it's clear. And more schematically, we write equation for xti. So xti is a monetary reserve of bank I, can be represented by drift component, B Lebesgue integral component, plus Brownian motion. In a process, standard Brownian motion, independent each other, and we have we want to describe the default and spike by this part. So x bar is the average, and we add new particles. So m is counting the number of defaults or the number of spikes over the time. So MTI is indicator such that tau ki is defined by such that xsi minus this one is negative. So the first bank is default, then everyone is drag. And because of this drag, or because of this negative effect, the other banks also is in danger of default. And in particular, if xs minus I, b minus this dragging effect, it becomes negative, then this particle I, other than the original I naught, is also default. So we count the number of tau ki as a default timing, and we consider cumulative number of defaults and cumulative number of spikes as m. So xti is added by the x bar. On the other hand, because of the default of the initial bank, we drag divide by the average amount of x bar, average amount of x bar, as well as this compensation term. Okay, so this is a model description. M bar, MM is a cumulative number of defaults by time t, and tau ki is a case default time for each bank I. Because once bank is default, then new bank is introduced, and this new bank has the same name, I, for simplicity. So tau ki is counting the number of default times for each bank I. We assume B is a globally elliptic continuous function on the space R to M, where X and M, So X is in R, and M is another R plus, has satisfied Lipschitz continuous condition, and also looking at the total summation is 0. So this is a situation that the total amount of the drift, which pushes the system going up, is 0. Okay, so this is a special situation. For example, if we take Bxm as minus A times x minus m, so m is coming from average. So let me go back one slide. So what is B? B contains X as well as X bar. So X represents bank's reservation of bank I, and X bar is the average. So the drift depends on the bank I as well as the average. If we look at the total sum of drift becomes 0, for example, Bxm is minus A is positive, X minus M. On this formulation, we get total sum of the drift becomes 0. Given a standard Brownian motion W, we consider the system X and M. And in particular, we are interested in that there might be multiple defaults at some time with positive probability. In other words, let's say there exists a pair I and J, there exists time t such that xdi and xdj are together at 0. And we want to see when this type of probability becomes positive. There's some technicality. If we replace 1 over n by 1 over n minus 1, this is just a small change. But so if we replace 1 over n by 1 over n minus 1, then we get here. In that case, we can check that at some point time t in the future, there exists all the banks at default together, even though we introduce a new banks with probability 1. So this is a slightly different model, but in this case, every bank is default. The reason why we consider this type of research is we are interested in systemic risk problems. So one bank is default, then this effect, negative effect, spreads over the society and the economy or banking system. And in particular, we are concerned about multiple defaults, so that we want to avoid multiple defaults if we can possible, if we can do it. So coming back to our original model, we have X bar, which is, so X bar is the average. Average is moving as a simple process. Brownian motion average plus 1 over n integral 0 t x bar dm bar. M bar is also the sample average of M over the banks. In between default times, X behaves as an n-dimensional diffusion with drift and unit diffusion coefficients. So when there is a default or jump in the process, the jump size of xdi can be written given by X bar because of the effect of the average times MTI minus MTI minus T minus this component. So we consider this particular system and similar setup with defaults and bars, intensity of banks. So here we consider bars and defaults of banks in terms of the physical hitting point. And simultaneously, the new bank is jumped into the system. On the other hand, maybe we can consider the system with default intensity. So that is another model, for example, and there are many researches on it. For example, we can see this paper. So we set up the model and we want to see if this solution exists. The solution to this stochastic differential equation exists. So to understand the solution, we set up physical solution first. Physical solution define a set value function gamma. So starting from gamma 0 and recursively define gamma k plus 1 from gamma k up to gamma k. And if xi minus x bar divided by n and the union of these guys is less than or equal to 0, then gamma k plus 1 is a set of new defaults bank. So gamma x as a union of gamma k, then a map defined by phi. Phi is an n-dimensional map, vector value function. Phi I of x is given by xi plus x bar times this quantity. And this explains how these defaults, multiple defaults, affect the system. Gamma is a set of defaulted banks, indexes, and phi is the spatial location after the defaults happening. So given the initial configuration, the starting point, and Brownian motion moving, and there's a strong solution until first time the default happens. The first time tau 1 is the first default time, and then at this moment, the system moves. So for each I is moving to this map, phi I. Then we repeat this procedure every time we have a default. Then we continue as a solution. So we continue from as yk plus 1, so that xi at tau k plus 1 is given by phi I of the yk plus 1, and mi is mi plus 1 indicator, so that we continue. So we piece together all the default times, the stochastic processes between default times. And x tau k0 is 0 for some k0, and we set tau l is tau 0 bar for every l greater than or equal to k0. In other words, tau 0 bar is the first time xs bar, the average, is hitting 0. In that case, we stop. Of course, everyone tracks to the 0. And this way, we construct the pair x and m. X is a monetary reserve in the banking system, and m is a number of defaults. As a proposition, given a standard Brownian motion W, the initial configuration, we say the process xm constructed by this physical solution is a unique strong solution on the time interval between 0 and tau 0 bar. If there is a default, then the post-default behavior is determined by the xdi at phi of I xt minus. The jump size of mj is given by this, so that we can make it works. Okay. And now let me move to the next question. When n becomes infinity. So n so far is fixed, but now we move to the situation such that the whole system, in the whole system, there are countably many, but now we consider n goes to infinity, the number of banks goes to infinity, then what happens? This part is coming from a Minifield approximation. So Minifield approximation, or theory of propagation of chaos, coming from McKean, Tanaka, and Delarue, Inglis, Rubenthaler and Tanre, and series of papers by Delarue, as well as Natochi and Shkolnikov, and other papers in the direction of Minifield games and Minifield situations in financial market. And here we consider as n goes to infinity the dynamics of the finite dimensional marginal distribution of limiting representative process. It can be formally written as this calligraphic X. So xt now becomes xs minus expectation if we take a drift function b as that example. So that example coming from this. So if we take this drift function b as minus a times x minus m, x is each bank's reserve minus m average, as n, the number of banks, is going to infinity, the sample average is going to the expectation by the law of large numbers. So the sample average becomes expectation of x of t, and we replace sample average by this and here, as well as sample average of the number of defaults is approximated by the expectation of m of s. If we take expectation of both sides, then what we have is that it becomes constant. So expectation of xt is expectation of x0, because expectation of xt, expectation of x0, expectation of xs are cancelled, and expectation of ms minus expectation of ms cancelled, so that expectation of xt becomes constant. If we start x0 as some particular point, x0 fixed constant, then we obtain this equation, and transforming the state space from 0 infinity to minus infinity to 1, then in other words, x hat is x naught, the initial position, minus xt divided by x net, x naught. Then we see x hat is behaving like this. We just change a variable from x to x hat, where w hat and m hat are given in this way. And this is very close, almost the same, to the stochastic process studied by Delarue, Inglis, Rubenthaler and Tanre, z hat t, which is x hat plus m hat. So that minus a, z hat minus m hat plus w hat plus expectation of m hat, where m hat is integer part of supremum of z hat. So if we write x hat and m hat and then add together, we call it z hat. And z hat, a positive part, supremum, running maximum of the positive part of z hat, and look at the integer part, then this is exactly m hat. So Delarue et al. Considered this type of stochastic process. And here, important observation is that m hat is integer part of supremum of z hat. So given so question is how to solve this Minifield equation, given a candidate solution ET for expectation. So let me call expectation m hat as a candidate ET. Then we consider z hat E given by the formula. Now we replace expectation by ET and recursively substitute one by one. Then if the limit exists or the map from the recursive iterations, has a fixed point, then we say the uniqueness of the solution is reduced to the uniqueness of the fixed point of MTE, the map, such that expected value of integer part of the running maxima is has a fixed point. So recursively define, starting from 0. So remember, ET is expectation. So if we replace expectation by ET and recursively substitute E0 is 0, En plus 1 becomes M of En, 1 by 1, then this is a monotone sequence because of the map, monotone sequence increasing over time, over the iterations. And we can consider the space of continuous functions, continuously differentiable function, such that the derivative is non-zero, increasing, starting from 0, and ET is less than or equal to the linear line of the slope 1 by x naught. And if a equals 0, we can write it more simple in a simpler way. Z hat becomes W hat plus E, so that MTE is given by this. What is W hat? W hat is a Brownian motion, original Brownian motion, W divided by X naught. And this one, MTE, is bounded by P of X naught. So for this special case, I present X naught is greater than 1 and A equals 0. For every E in this space, we have MEs in L. So because we have a monotonicity, En is less than or equal to E of n plus 1. And if we repeat these iterations, we say ET star exists and it satisfies MTE star as a fixed point. So numerical example shows if A is 0 and X naught is 1, then starting from 0 and then the first one is a red curve, and the next one is green, blue, light green, light blue, and so on, then it converges to this curve. And this is a curve which represents E star of t, which has a fixed point. In other words, a solution to this original Minifield equation of this type. So we discussed briefly about the connection. So connection to Delarue, Inglis, et al., as well as we have a connection to Caceres, Carrillo, and Perelstam. Consider the nonlinear Martin-Brasov stochastic differential equation of this type. And then we have W hat plus ET and integral Z hat minus M hat. So this is very similar, we consider, and there they had C here, and here we have 1. So C in their papers, they look at C is between 0 and 1. Here we have coefficient 1. If we look at the perspective of partial differential equations, we can describe a blow-up phenomena. So we consider this Martin-Brasov equation. Consider the density or PTX of the solution. This density should satisfy the Fokker-Planck equation. And we have ET dot, which is a derivative of density, which indicates the slope. So ET dot is expected defaults number. The number of defaults has increased with rate ET dot. So ET dot is a differential of expected default times default number. And theorem, suppose that alpha equals 1 and expectation of xt is x naught, and then there exists mu such that this quantity, initial position, initial density P0x satisfies this condition, then there is no global in time weak solution. In other words, the solution of this Fokker-Planck equation blows up. And we want to avoid such situation. And moreover, we can consider the stationary distribution of xt, which has a density px, which is stationary density because of this Ornstein-Uhlenbeck mean departing phenomena comes from this drift component, and it is a stationary, it has an invariant distribution which has a density of this type. And this can be considered from Fokker-Planck equation, stationary solution of Fokker-Planck equation, and interestingly, we can write it explicitly. What is C naught here? C naught is a limiting default rate. Limiting default rate is determined by x naught, and this unique solution of this equation. In particular, when a equals 0, in that case, this part is 0. Then we can write it quite simply. C0 is 1 over x naught square, and we can write it in terms of exponential function. And this is the stationary solution. This stationary solution comes from this Fokker-Planck equation, partial differential equation consideration. Now we want to introduce Minifield game perspective. So representative bank we consider as a nonlinear equation, stochastic differential equation. And each player bank controls the drift, borrowing and bending to the central bank to minimize the running cost and interacts through two Minifield terms. So the first Minifield term is average of both, and another Minifield term is coming from the rate of the default. So for each smooth probability density M, we consider two operators. So we have M. M is a density function on the positive half line. We consider two operators, M of M, which is expectation, and E of M. E of M is the derivative derivative at the origin. And control of each player bank, each bank is, let me call it Xi. And so now we replace drift component by Xi plus original component, as well as EM and MN. And we consider running cost as quadratic function. So fxmxc is control plot square, quadratic control, linear quadratic control problem. And the resulting Minifield Nash equilibrium is x tilde. So now we extended the model to the game or control problem. So we have a drift component which has x tilde, the distribution, as well as control part. And to solve it, we consider a flow of probability density M and control C, and then we minimize the running cost. So this is the running cost, and we want to minimize until tau M, in other words, this resulting procedure from the Minifield limit. So we consider the representative bank hitting the origin we call tau MC. And we want to see fixed point M, which solves this Nash equilibrium. Following Lauriere and Lyons, we have a Fokker-Planck equation and HAB equation, which has described by Hamiltonian H. The Hamiltonian H, X and P is defined by, we want to see infimum of drift times P plus running cost. So in this case, in our case, we set up in a nice way so that we have half of P minus phi square minus this quantity. To solve this Minifield game, we consider a numerical scheme. So we start with a partition of the time and the space. Time is between 0 and t, and space is between 0 and L. And we consider mesh size, delta t, which is t over nt. Nt is a number of points in time, and h is a number of points in the space. And we split the space into the mesh. And at each grid, we consider ui, u, tn, xi, and mi, m. And we consider m of mn. So m is here, mmn and emn, and we present those phi and psi in the previous page as phi tilde and psi tilde. And to introduce discrete Hamiltonian, which is given by h tilde. H tilde is half of h tilde square 1 h to the square of 2 minus psi tilde. So this is a discrete version of Hamiltonian. And h tilde belongs to C1 and is consistent with the value of h with piecewise linear interpolation of M. And discrete HAB equation, so HAB equation in the continuous version we represented here. And discrete version is given by this, where dt and delta h are the first and the second order finite difference operator. So we consider finite difference method of solving Minifield game. Discrete version of Fokker-Planck equation is given by dtm, Laplacian component, discrete Laplacian, and bi and beta. Bi is given by this, and beta is given by that. So then numerical scheme is the following. So starting with initial values, solve discrete Fokker-Planck equation recursively for Mn. And then by Newton method, we consider discrete HAB equation and repeat for k equals 0, 1, 2, etc. until the difference or error term becomes small, sufficiently small. Numerical results for different parameter sets, and we have so we consider different values of A, different values of initial values, and R is a discounting factor interest rate, and we consider the diffusion coefficient sigma. Sigma is 1, and that's what we discussed so far, but we can introduce sigma is not necessarily 1. In that case, we get 0.8. We have a curve of the purple line, purple curve. So this is a final density at time t, and mean field value, which is given by this MMT, and default rate E of MT is given by these curves. Time evolution of MTX and UTX is given by, so this is a timeline starting from time 0 over time, starting from this concentration of this part, and then as t goes to from 0 to the positive side, the density MTX decreasing like this, and UTX is moving from this curve to this curve over the time. And then we can look at the stationary mean field game with default costs. So for comparison, we consider a stationary regime with default cost gamma, and the representative bank minimizing the cost. And for the stationary case, so we consider the stationary solution of HAB Fokker-Planck equation. So previously we have a time derivative is set to 0. Question is, what is a stationary solution for this mean field game? Then, which is given by, we have ansatz UX, and A over 2, the quadratic, and linear component, and constant term. And then substitute this ansatz into HAB equation and solve for A and B, and the delta and C. So delta is coming to in here, and C is a constant term. And if gamma M has this particular form, then you put gamma equals 1 minus A over this ratio, then the resulting stationary measure M should satisfy the Fokker-Planck equation of this type. But now this Fokker-Planck equation is a form we considered before, which is here. For the Fokker-Planck equation without control, we consider a stationary solution for this process. And because without control, we have just a constant A. Now we have a control, but because of the stationary regime, the control is given by constant term, so that we can say the solution should satisfy this Fokker-Planck equation. And it has a closed form solution as in the previous discussion. And the corresponding control is given by xi hat minus the derivative component, which has this form. So let me summarize what I have presented. So annihilation or default and spike regulation are considered in the banking system. We consider physical solution and Minifield limit. We consider fixed point and connection to neuron spike modeling of Delarue et al. And open problem is to justify mathematically the limiting quantity is indeed a nonlinear Mackin-Brasov equation. And we also consider stationary distribution, stationary solution of this problem, in particular Minifield optimization, numerical simulations, and partial differential equations. This is a PhD thesis of Matthew Lauriere, coming from a PhD thesis of Matthew Lauriere. And part of research is supported by grants, National Science Foundation grants. And thank you very much for your attention.
Thank you very much, Tomoyuki. And if you have a question, please raise your hand. Meanwhile, I can start with the first question, and it's related to the beginning of the talk. How do you consider the importance of the size of on each bank in the system? I mean, I think this is related with the function B you mentioned at the beginning.
Yes, so we consider, so this is a mathematical representation, and I'm interested in this type of systemic risk problems. When I was a student, as a PhD student, about 10 years ago, there was a financial crisis about 2008, 2007. People are suffering from the financial crisis. And the financial crisis mathematically can be seen. This is only what I presented today is capturing only one aspect, a particular aspect of the financial crisis. But this modeling or understanding of the behaviors of many, many people, like a large banking system, is quite important because modeling can give us some insights and the future perspectives. So doing mathematical analysis provides understanding of the future, what will be going to happen. So in that sense, although this is, again, it is a mathematical caricature and the simplification of the reality, it's quite far from the reality. However, I think as mathematicians, applied mathematicians or statisticians, we should seek for the future and the explanations of what's going on. And we also need data. I didn't present anything about the data today, but I think the data, incorporating the data and also the methods from the data science is quite important. And combined together with the data, mathematical analysis can fly.
Thank you, okay. Well, I don't know if someone have a question or some panelist.
I have a question myself, Mauricio. Yes, I would like to know actually why you deal with a concept of physical solution, in the sense that you are dealing with a financial model. Maybe there is some notion of solution that should be relevant in this case rather than a solution related to physics.
Yes, so that's a good question. The important thing I should have mentioned, but I didn't mention, is that this usually in practice, there is some delay. So one bank defaults, one bank is default, and then this negative affects the next bank and the next bank and so on. But there is some time lag. Here we consider ideal situation that this negative effect spreads immediately. That is a quite ideal situation. More realistically, we can consider delay of these effects. So there's some one bank is default, then this negative effects affect the next bank or the whole banking system with some delays. Here we consider physical solution because mathematical description of a banking system, it depends on the particle system, and there are some studies of particle systems, and there people, physicians, call the physical solutions. So that's why I call it physical solutions, but this is, I think, more or less it's a mathematical description of the solution in instantaneous effects of the defaults.
I see. Thank you.
Thank you.
Thank you. Please, Professor Storm.
One question, I'm not sure if I completely understood it, but in your current model, if I understood this correctly, basically every time a bank is defaulting, you have basically a new bank born exactly with average capital.
Yes, so new bank is coming to the average. So the total number of banks is constant in the finite n system, and which makes the system much easier to be handled. As well as the average and the choice of the new location of the new bank is quite arbitrary. It comes into the average, maybe not necessarily the average. I understand your question, but in the particular system we consider is going to be average, so that in the limit the system becomes stable or stationary. If we modify the position of the new bank when it comes into the system, if we change the position from average to somewhere else, then in the limit we have to take care of this modification. So Stefan's question is important. How we understand this modification, the perturbation from this quite idealistic presentation to the perturbed, to the different kinds of changes. I think that's important, and the reason why we consider numerical scheme is that we want to understand the effect of perturbations, and parameter changes affect the whole system, I think, and we haven't explored all the possibilities yet, but we should think about perturbations of the system so that we can see different kinds of behaviors. Thank you for your question, Stefan.
Okay, if your question is answered, I think Ioannis have a question also.
Thank you very much, Ichiba, for the wonderful presentation. I just wanted to tell you that you have an accumulator that evolves, and recording the history and the changes and the shocks that are happening. But how about if a loss is greater than the average? What's happening then?
So if the loss is greater than the average, that's a good question. So here the loss is coming, we describe the loss of the bank of default as just the monetary reserve, but we should consider the asset part and the debt, right? When we discuss the real portfolio of the banks, we need to consider asset and debt, right, all together. Here we only consider the amount of cash. So that's the difference. I think your point is very important. We should consider, and there are some research I should have mentioned, consider both parts and asset and debt all together, asset, debt, and capital all together in the balance sheet. What I presented here is quite far from the reality. We have to consider the real part. Like,
Thank you very much.
Point.
Thank you. Thank you. Someone else have a question? Okay, if not, we'd like to thank Tomoyuki Ichiba. Thank you very much, Professor, for your talk.
Thank you very much.